Hello everyone, my name is Vangelis Velkastritis and I am customer service engineer at Beta SE Systems. I would like to welcome you in this webinar about the latest developments in Nanza for composites. Today's presentation is divided in two sections. The first is dedicated to laminated composites. And specifically enhancements in the Laminate Convert plugin, cross sections calculation for laminates, laminate plybook generation, and a new function that converts a solid into a cell laminate. Afterwards, we are going to see solutions for multi-scale material modeling of composites, for the mean field homogenization, and FE homogenization. All the function will be shown through slides and will be followed by live demo. Starting with the Laminate Convert Advanced plugin, we have a new structure type that is supported. This is the sandwich structure. Selecting this type of structure will convert the cell laminate into cell, solid, and cell structure that will simulate the sandwich. Moreover, the cell to solid interfaces can be modeled with common node interface, beam elements, cohesive elements, and contact pairs. So let's see this example in Nanza. Okay, so here we have a model of the hood that is composed by a laminate property, a cell laminate property. If I open the laminate tool, I can see that I have 7 layers defined, 3 layers for at the top, a core material, which is also a thickest layer, and some other UD layers at the top. So if I go to the plugins Laminate Convert Advanced, I will select the cell elements, and I can go here to the structure and select the sandwich. Now, by selecting this type of structure, automatically the thickest layer becomes the core layer, that it will be represented by solid elements. So for this solid layer of the core, I can also specify the solid rows that are going to be created. From here, I can specify the interface between the top and bottom flanges of the sandwich structure. And by pressing OK, I get this result. Where I have a cell laminate for the top, the solid core, and a cell laminate at the bottom. If I open again the laminate tool, I can see that I have one laminate with the 3 layers at the bottom, the solid core laminate, and 3 and a laminate with 3 layers at the bottom. Moving on, the cross-section calculation for laminated models is now available. The new FE crossover can calculate the cross-sectional properties of a laminated cell model. The solver will take into account the layered structure of the laminate and the anisotropy of the materials that are used by the layers. So in this way, a more accurate result is calculated for laminated cross sections. Okay, let's see that example in Nanza. Okay, so here I have a model that is consisted by a laminate property. I will do a cut here and switch to the laminate view. So this, sorry, the lamination looks like this. And I will perform a multicut on this cell model. I will select this curve. Okay. The cell elements that are going to be cut. And the important thing here is to open the options list and switch the crossover to FE. I will create 10 beams, delete the replaced cut entities, and connect with RB2 elements. So now the multicut is taking place. The cross sections are created. And if I switch to the cross menu, I can see the results. There is a reference material, so the cross section is treated as a non-homogeneous cross section. And this is how I get the cross-section results, taking into account the anisotropy and the heterogeneity through the thickness for this laminate model. Okay, moving on. The playbook generation is now available for laminate properties. Through the laminate tool, a PowerPoint report with the playbook of the laminate property can be generated. And additionally, the option to create and output the flat pattern curves in IGS format is available. Let's see that also. So I have this laminate model. Can open the laminate tool. And I can see that I have 14 layers defined. and that these layers are draped. Their drape status is okay. Since they have been draped in ANSA, I can go to the settings and activate the show flat pattern option, and I can see if I'm switching, if I'm picking a layer from list, it's a flat pattern. So the flat pattern is actually the opposite result of the drape. So uh, if this is the initial pattern of the layer, and if it is draped starting from this point, which is the rosette, if it is draped around this geometry, I will get the result that the drape has calculated. Moreover, I can go to the laminate property, go to generate plybook. I can specify a PowerPoint file. I have some options here for the views because screenshots are going to be taken. And I have the option for the transparent view, and I can also output the flat patterned curves. I need first to add them in a group, okay, as IGS files. So if I press OK, the PowerPoint report will be created. It will have it will be actually the playbook. It will have the flat patterns of each layer and the attributes of the layers. So the PowerPoint will look like this. I have the materials that are defined, and for each layer, I have the attributes of the layer and the flat pattern, as well as the draped result shown for every layer. Okay. Additionally, free geometry curves are created for every flat pattern. So I have the regions, the region of the flat pattern as a curve, and I can export it in a IGS format. Okay. A new function that converts solid laminate to cell laminate is available through the laminate tool. This conversion can be done for both single element solid laminates or solid laminates that have per ply stacking definitions. We will see also an example. So in this example, we have two solid laminate definitions. The one is the per-ply model, so its layer here is a solid row, and the other is with a single element. So there is a single element for the property, and the lamination is the lamination information is inside this solid property. So the layers are defined inside the single solid, and the other example is the per-ply laminate model. I can select them both and press the unvolumize. I can delete the original solids and treat the initial conditions if there are. And by pressing OK, I am having to sell laminate properties with the layer definitions accordingly. So this is the opposite of laminate convert, we could say. Let's move now to the multi-scale modeling approach, which is an approach that is used for the composite material characterization. ANSA offered functionality for both milled-field homogenization and FE homogenization methods. The homogenization tool of ANSA is used for the mean field homogenization, and it can perform linear and non-linear material modeling of heterogeneous composite materials. The tool supports several semi-analytical methods for the estimation of the constitutive law for the composite based on the properties of the constituents. From this material model that is being estimated, the solver material entity card will be created and used in the FE model. Furthermore, the homogenization tool can be also coupled with Abaqus solver through UMAT and VUMAT subroutines that called during the solutions, during the FE solution, and perform the mean field homogenization. Let's see the homogenization tool in ANSA. So let me switch to Abaqus deck. Okay. The homogenization tool is accessible from the materials list by the context menu, new by homogenization. So this is the overview of the homogenization tool. On the top side of the window, we have the analysis option, where the user can select the material model that he wants to estimate for the composite material. Then the homogenization method can be selected. The most advanced and suggested mean field homogenization method is the multi-step homogenization. And on this side of the window, the user must specify the properties of the matrix. So the composite has two main constituents, the matrix and the inclusion. Of course, the inclusions can be multiple, but the matrix is always one. So the properties of the matrix are set here. As you can see, here I have the elastic thermal, and I have also tabs for plastic damage and others. These tabs are activated according to the material model that is selected. So if I switch this to the elastoplastic material, I also need to specify the plastic behavior of the matrix. At this side of the homogenization tool, we have the inclusions list. So from this button here, I can create inclusions. Again, for the inclusion, I need the mechanical properties. But apart from this, I also need the shape of the inclusion and the orientation inside the matrix. So the shape is given in terms of an ellipsoid. So by setting the lengths of the three axes of the ellipsoid, I have the shape of the inclusion. And the orientation tensor that can be given through spherical coordinates or through an orientation tensor. Once the settings have been specified, they can be saved into an XML format and accessed by the tool. Now, once I have specified the material model and the properties for matrix and inclusion, of course, I need to specify the volume fraction of the inclusion, so I can have multiple inclusions defined, and I can enable more than one inclusions inside the volume of the matrix. So I need also to specify the volume fraction and enable an inclusion, so it takes part in the composite. And once I have set my composite, I press the results button and get the results of the homogenization. So the result of the mean field homogenization is this homogenized stiffness tensor. The method takes into account both the properties, the shape and the orientation, and the volume fraction of the inclusion, and estimates the homogenized stiffness tensor. From this homogenized stiffness tensor, the tool will also estimate the degree of anisotropy. So in this case, we have spherical particles, because the ellipsoid has the same value in the three directions, in the three axes. So we ended up with an isotropic material. So this was expected. So if I change this, or let me create a new. If I create a new inclusion that is long fiber and press results, since I have long fibers inside the matrix, I will get a transversely isotropic material. So the tool also estimates the degree of anisotropy. Now, once I have done the homogenization, the next step is to create the material entity. So according to the homogenized stiffness tensor that it has been calculated, the engineering properties are calculated and are calculated, and they are assigned to the material card, to the corresponding material card. So for this example with the long fiber, the material that is about to be created for Abaqus, has elastic type engineering constants because it is transversely isotropic. If I enable the spherical inclusion, I will lend to a material, an isotropic material. So according to the material that it has been estimated, the corresponding entity is created. Now, especially for Abaqus, as we said, and before that, let's see also an example with a nonlinear material model. Okay. So, in case we want to estimate the nonlinear behavior of the composite, we can specify the respective material model, specify the plastic properties for the matrix. The inclusion can be also plastic, but in most of the cases, the matrix has the plasticity. And apart from the matrix properties, in case of nonlinear materials, we need also to specify a loading condition, a general 3D, for example, where we need to apply some strains in order to capture the nonlinear behavior of the composite. So I will press here results. These are the linear results. And if I switch to plastic, I can also see the plastic results. So I will plot here the von Mises versus the strain that I have specified in the loading. So this is the composite, this is the matrix, and this is the inclusion. So as you can see here, I have the tool has estimated the elastoplastic behavior for the composite based on the response of the two constituents, the matrix and the inclusion. The loading is necessary because what actually the tool does is that it adds some strain incrementally, so it can capture and performs homogenization at every increment, so it can capture the nonlinearity for the homogenized material. Once the nonlinear material, the elastoplastic material has been calculated, I can press make material, and I'm prompted to select elastic or isotropic elastoplastic material with isotropic hardening. So this will disregard any nonlinearity. I don't need that. I will select isotropic with elastoplastic hardening. So the material that will be created needs a curve to be assigned, a curve that will describe the nonlinearity. So I will add the von Mises curve of the composite. And the Young modulus is automatically calculated from the linear part of the curve. I need to specify the Poisson ratio, and by pressing finish, I can see that it has created the Abaqus isotropic material with the star elastic here, and the star plastic has isotropic hardening and refers to a data table where I can see the plasticity part of the curve. And this is a nonlinear homogenized material. Now, especially for Abaqus, we distribute some UMAT and the VUMAT subroutines. So there is an option available in the Linux OS where it will create the UMAT. So by pressing make UMAT, it creates the corresponding depvar and user material keywords that are needed actually that are needed for the UMAT for the subroutines. So the constants here that are given to the subroutines are actually the settings of the homogenization tool. So all the settings about the material model that is selected, the matrix properties, the inclusion properties are given in a specific format that is created by pressing the Make UMAT button, and during output, the Abacus environment that it will be also be created, and this Abacus will have the path where actually the installation folder where we our subroutines are located. So let's see an example. Okay, so this is a simply supported plate with a pressure load in the middle. Okay, for this model, there is this material with the user and the depvar defined, and this model has been solved with Abacus using the subroutines that we offer. So if we go in Meta, now, so if we output this model with the UMAT material that has been assigned to the solid elements, and if we also have the SDV output requests, we will get the results of the UMAT subroutine. So we will have the solution dependent variables. So if we go to Meta, you can see that we have all these solution dependent variables coming from the UMAT. They are stored in the ODB. So for this model, I will load the stress component at the X direction, and I will also load the strains, and moreover the stresses at the 1-1 direction for the fiber, and the stresses at the same direction for the matrix. Okay. Sorry, let me fix that. Okay. So if I now see, I focus on an element and see what has been calculated by the solver through the UMAT. I will plot all the stresses for the matrix, the fiber, and the homogenized versus the strains. Okay. And I get something like this. So in this way, we have solved a macro scale model, but with the use of UMAT, we have also results of the at the microstructure level. So this is the advantage of using the UMAT, the performing mean field homogenization during solution. Actually, what the UMAT subroutine does is that it performs this multi-step homogenization at every increment of the Abaqus solution. So in this way, we are sure we have full detail of the microstructural behavior, and we ensure that the material model follows the loading path during the solution. Okay. Now, let's see now the FE homogenization. For FE homogenization, the homogenization tool can be used for the generation and setup of the RV model. The RV model is the microstructure FE model of a multi-phase composite material. And from that tool, it can be created automatically and or it can be imported in the homogenization tool. Furthermore, the RV can be set up for FE homogenization analysis, and once it is solved, it can be post-treated for the estimation of the homogenized material response. Here you can see some types of RV that are generated. The tool can create continuous fiber RVs such as woven or long or unidirectional. It can create short fiber RVs and multi-layer RVs. Now let's see. Let's see that in ANSA. Okay, so the RV generation is done through the RV options tab. So once the matrix and inclusions are specified, I can go to the RV options tab and select what type of RV I want to create. So the first tab has to do with short fiber RVs. So this is a type of RV with short particles. It can be fibers or particles. This depends on the shape of the inclusion. Mind that here we need to specify the shape of the ellipsoid according to have dimensions that are according to the global geometry resolution and mesh parameters because the tool will create mesh, so here the values must be consistent with my mesh parameters. Okay. And so the short fiber RV will have the particles inside the volume. The parameter here that I want to specify is the size of the RV. It will create a cube, actually. I have the option to create a periodic geometry. So, okay. If I press preview here, I get a quick preview of what is going to be created. So this will create something like this one. I can change the RV size, okay, and have something like this. Next is the continuous fiber RV. So if I select here from this tab here, I can create unidirectional RVs or woven RVs. These are predefined shapes. So regardless the inclusion that the shape of the inclusion that I have selected for the composite, using this will create one of the two predefined shapes, unidirectional or woven. And also there is the option to create multi-layer RVs. Once the RV is generated, is previewed actually. I must press the preview button, so it is stored in the memory. I can switch to the generate tab and generate the RV from scratch. So I have the option to create contacts at the interface between the matrix and the inclusion. And I can also create periodic boundary conditions. So this will also create periodic boundary conditions and the step so it can be ready to run for Abacus. Additionally, if I have the RV generated from another tool or I have created in a previous ANSA session, I can attach this to the RV tool and I can perform some actions. So for an already created RV, I can mesh it if it is just geometry, or I can apply the boundary conditions. So I can do the same as generate also for RVs that are not created by the tool. And once I have an RV solved, so I can also post-process it to estimate the average. I can post-process it to estimate the average response and which is the response of the homogenized material. So let's see an example. So here I have a woven RV. I can open the homogenization tool. Let me clear this. Okay. Go to the external RV tab, hit the question mark, and attach this to the homogenization tool. So the tool recognized the dimensions of the RV. Mind that the RV must be placed at the origin of the model. It is a meshed RV, and the actions that I can perform is that I can apply the periodic boundary conditions. So if I press here, okay, let me show you. apart from during the attachment that I did on the homogenization tool, the tool also recognized the matrix properties and the inclusion properties, and as well as the volume fraction. Okay. So if I press now here apply, okay, the tool has created the periodic boundary conditions for Abaqus. It has also created the step, and now this model is ready to run. I can output it and solve it with Abaqus. I have this example solved. Let's see that. Okay. So this has been solved by Abaqus. And I can see the stresses and how it deforms. So at this stage, I just want the average response of this model to get the homogenized material properties. So this is the purpose actually of the FE homogenization, to estimate the material properties based on the response of this FE. Since I have this model solved, I will input this in ANSA. I will go to the homogenization tool, external RVE, and I will attach this RVE. Okay. And since I have also the ODB, I will go to the post-process section here, hit the question mark, select the file that has been solved. On this folder, I have also the ODB with the same name, open, and I will press apply. So now the tool will run a meta session that will do the averaging of the stresses in the matrix and the fibers, and will estimate the homogenized behavior. Okay. So this is the result with the three curves. The matrix, the fiber, and the homogenized behavior. From here, I can press make material, select the curve, specify the Poisson ratio, and the material will be created. So this is the FE homogenization. For Nastran deck, if I am in Nastran deck, the homogenization can be done directly in ANSA. With epilisis. So I can attach an external RV again. And this option also for solve and FE homogenization is available. So for this example, I will create the boundary conditions for FE homogenization. The material is that I expect will be orthotropic, since it is a woven. And the periodic boundary conditions that will created for epilysis will actually subject the RV into the loading at the three axes, so I will get the orthotropic behavior. If I press apply, the periodic boundary conditions are applied and the model is sent to epilysis. It's solved by epilysis, and then the same post-treatment takes place. The average response of the RV is estimated, and the material properties are assigned. Finally, the coupling of molding and simulations with structural simulations for FRP's Fabry Plus plastics is available through the results mapper tool. It is a common case that we have results with the material orientation coming from a MoldX 3D or a mold flow analysis. And through the results mapper tool, we can map the orientations and at the same time perform homogenization, mean field homogenization, with the orientation tensor that comes from the molding analysis. This functionality is available for Abaqus and LS-DYNA. Let's see. Sorry. Okay, so I have this example. I have the material orientation of this model from MoldX analysis and the MoldX O2D file that contains the material orientation for each element. And there is the option here to perform homogenization. If I go here, homogenization options, I can specify the matrix and fiber properties. And I have the option to perform homogenization inside ANSA or outside ANSA. What does this mean? This means that in case this is checked, it will create the MAT 157 for LS-DYNA combined with the initial stress keywords where the history variables are assigned. And if I do it out of ANSA, it will create the MAT 215 material. So you can create two types. I will leave it like this, press OK, and apply. So right now, the material orientation comes and is being mapped at the target model. And for every element, the mean field homogenization takes place according to the orientation, to the material orientation that comes from the mapping. So in this way, we have it is like we estimate one material per. It's like we estimate one material for each element. Okay, so these are the orientations. And the information of the homogenized material for Dyna is inside this initial stress solid keyword. So in this keyword, let's see also the material. So the material 157 is created, and this material also wants as input this initial stress keyword with the history variables that have the material orientation of this element and the homogenized stiffness tensor, a homogenized material actually, for this specific element. I will erase this. Let me. This is also available for Abacus. But for Abacus, the definition is quite more straightforward, since the Abacus supports distribution table, the distribution table keyword for elements and materials. So it actually creates a distribution table, and as you can see, the information of the material of its element in ANSA is shown in the material card. So this is the material, the homogenized material that has been calculated during the mapping for this solid element.